And I'll do this maneuver. Okay, very good. I think I've got 3 monitors open, but I can never get my everything to appear as I want it to. Okay, so we're talking about the Mann-Whitney U-test tonight, the Wilcoxon signed ranks test, and the Kruskal-Wallis H-test, which, as you know by now, are the non-parametric equivalents to, respectively, the independent t-test, the dependent t-test, and the one-way ANOVA, which you've already learned about. And these tests are also called distribution-free tests because in addition to being appropriate when you have ordinal type data, ordinal scale of measurement, you can also violate assumptions of normal distribution of the population data, which sometimes we do. Sometimes we have skewed data in the population, so normal parametric tests are not appropriate. So we're going to go over 3 problems tonight, each associated with these different tests, and we'll talk about them and their rationale and so on. Okay, so our first problem, we'll start off with something food related. Some of you are eating while you're doing class, some of you are waiting. That's fine. A chef knows there are 2 kinds of olive oil, regular and extra virgin, which is made from select olives and cold processed. Extra virgin oil is therefore more expensive than regular olive oil, but it also tastes better. How many of you cook with olive oil? See, like 20 years ago, not many people did that, but now it's the healthy way to go. You can't just use regular vegetable oil or corn oil. That is so 1980s. So we use olive oil now. He wants to know whether to use extra virgin oil in his salad dressing. It's going to be more expensive, but it tastes better. To decide, he recruits 28 volunteers. He prepares identical salads and salad dressing for all. But for a randomly selected 14, he uses extra virgin oil. The remainder get regular oil. He asks all 28 to rate his salad dressing on a 10-point scale, with 10 being excellent, 0 would be terrible. The ratings are shown below. Does extra virgin oil improve the salad dressing? So this should seem similar to an independent t-test in the sense that we have independent groups. That is, the data shown for the regular group is not connected, paired, related in any way to the scores that we have in the extra virgin group. And that's what we mean by independent samples, by independency here, that we have a between subjects design where people are put into different groups. They're not related or connected in any way, and we're simply comparing them. And if we use random assignment, we can usually control for a lot of what are called threats to internal validity. And one of those especially is selection bias. We're going to talk about all this stuff in the next class, which is research methods. So hopefully there'll be some connection to the two here. But the big thing about this problem is we have ratings. And typically ratings are not as precise in measurement as typical interval ratio scale of measurement data, like test scores or weight or height or something like that. When we ask individuals to rate something on a 10-point scale, we would be making huge assumptions about whether the difference between a 6 and a 7 is the same as the difference between a 2 and a 3. And so because we don't have that precise measurement, all we can say is that a 7 represents something more than a 6. We have violated an important assumption of the independent t-test, which is interval ratio data. So we'll use a non-parametric equivalent to the independent samples t-test here. So we're going to use what's called the Mann-Whitney U-test. Now, these have weird names. One, if you're the statistician that develops them, typically you get to name the test. So Mann and Whitney developed this. They also came up with a U calculation that is sort of, it's not really the test statistic, but it is the greater of 2 U values. There's a U1 and a U2. And for many years, I showed students how to compute these by hand, so to speak. We give them a formula, show how to do all these calculations. But after, the advent of calculators and especially web-based calculators, there's really no reason for that because even though some of you, a very small percentage, might really appreciate, like, oh, so that's how you do it. That's how the computer gets it. You're probably never going to compute one of these by hand. And I don't see any reason for you to learn that as part of this class. What I want you to know is the rationale behind statistical tests, and most importantly, the ultimate goal, and I think one of the most important goals of this program overall, is to teach you to not be taken advantage of, to empower you, to give you an understanding of statistics and numbers. So when people throw things at you, which a majority of the time is something I would call BS, and it doesn't stand for that, it calls for bunk science. Um, it's a load of you know what. You can say, hey, I know a little bit about statistics. I know a little bit about research. I know a little bit about debunking. I don't buy that stuff. Show me the evidence. So, okay, so here we go. Mann-Whitney U-test. So we have ordinal data and we want to compare two independent samples. Can't use the independent samples t-test because of an assumption violation. The Mann-Whitney is the non-parametric alternative to the independent samples t-test. But then, as you also read, we have less statistical power. Non-parametric tests, like ordinal compared to interval ratio data, is less precise, and we typically end up with less statistical power. And as you know, statistical power is your ability to reject the null hypothesis, assuming that in the population, the null hypothesis is indeed false. So if we have a difference out there in the population, and we want to be able to find that difference, we want to use the most powerful statistical test available without violating any assumptions. Because once we violate assumptions, and if we used a typical independent t-test here, we would have the problem of inflated type 1 error rate, which means finding a difference when there might actually not be one. So we're dealing with two things here, possibly less statistical power when there is a difference, and inflated type 1 error if there isn't a difference. Well, what if we just know that there is a difference or there isn't? We don't. That's why we do the study and the statistical test in the first place. All right, so here we go. The Mann-Whitney can be used to follow up a significant t-test if there is concern that assumptions may have been violated. So that's an important piece of advice for you here. If you're ever going to be doing research in the future or reading about it, if you see that somebody did an independent t-test or a ANOVA or something, you're like, hey, that's ratings data. I think that violates an assumption. You can always do a non-parametric follow-up or the equivalent to that test. And if the t-test or a ANOVA rejects the null hypothesis and finds statistical significance and finds a difference, but the non-parametric version does not, you could say, hey, we've got a possible type 1 error here. And most people won't have any idea what a type 1 error is, but you can sound very intelligent and just say, hey, stupid, that's a type 1 error. You can't pass that kind of stuff as research. You might not want to use the word stupid. You'll get fired. Okay. So the Mann-Whitney U-test, the null hypothesis is always the same with a Mann-Whitney U-test. It is there is no difference between the two population mean ranks. We'll be computing ranks here when we do this data. And for this particular problem, we'll be rank ordering all of those scores from lowest to highest. And then we assign ranks to those data. So like if the lowest score is 0, that gets a rank of 1. If the highest score is 25, that gets a rank of whatever n equals. And when we have tied ranks, we average those ranks and divide them and find the mean of the tied ranks. And again, you don't ever have to do any of that, so there's no reason for us to go through that process. The alternative hypothesis for a two-tailed test will be the two population mean ranks are not equal. You can do a one-tailed test with these non-parametric tests, just like you can parametric. If you have a strong assumption or reason up front that it should be one-tailed, if you know that Well, of course, extra virgin olive oil is going to taste better and not worse than normal olive oil. Then you could do a one-tailed test. But in this case, we don't know, or we just simply want to be conservative. It's possible that people might want that junk, right? The old dressing. For example, let's say that your significant other thinks that you don't really have much of a taste in chocolate, and I'll bet that you like chocolate that you can purchase at like the local grocery store better than like Swiss chocolate or Belgian chocolate or something like that. So they give you a blind taste test. It's possible you might want the other stuff and think it's better simply because you're more familiar with that, because you've been eating that your whole life. That's associated with good memories, and you rank that higher. So it's not always so much a matter of, oh, this is definitely better, this one's not. Sometimes when you have amateurs doing the taste tests and ratings, things like that, they're making judgments based on familiarity, not so much like a wine taster would do, like, boy, I really like the oak flavor in this. Most people drink wine like, yep, that's good enough. What's that? $5 a bottle? That works for me. All right. Okay. So we'll use an alpha 0.05. And degrees of freedom, we're going to be using a Z distribution. A Z distribution is similar to a T distribution, except that it's really normally distributed. And that's just the distribution of the test statistic in the population that we're going to use to determine significance. All right, so we find if we compute mean ranks for the both two sets of scores, that is, average all the rank scores for each of the groups, we find a mean rank for the regular to be 13 and a mean rank for the extra virgin to be 16. Now, Vassar Stats is going to show us this, but it's important for you when you look at those mean ranks to know which one means higher scores and which one means lower scores. Well, luckily for us, it's the same. The higher the mean rank, the higher the overall scores were. The lower the mean rank, the lower. So all this tells you is that one's 16 and one's 13. If we find a significant difference, that means that they overall gave higher rankings or higher ratings for the extra virgin olive oil salad dressing, and they gave lower ratings for the regular olive oil salad dressing. That's all it means. Remember, this is important though, because it's one thing to know the statistical tests, but when you are taking a test or in real life, when you get to the problem, they're going to say, all right, you conduct the statistical test. What's the conclusion? Well, the conclusion is by far the very most important part of this. And you've got to be able to know how to reach the correct conclusion given what your output is. Okay, so this means extra virgin was ranked higher descriptively. Now, when we run the test, we'll know statistically whether it was higher. So we run the test, we find we get a Z value of 0.92, a probability two-tailed of 0.3576. That's not lower than 0.05. And so our conclusion in this case would be there is no difference. The chef might as well save money and buy the cheaper olive oil because most of his customers can't really tell the difference. See, it all depends on whether you're working at like a Michelin classified restaurant, fancy in a big city, and do I need to use the best ingredients? Or am I serving, chicken wings on a Thursday night for $1 a piece to my local restaurant establishment? Those folks there probably don't really have a discerning palate. They're looking more for cost savings. I can use the cheaper stuff. Maybe I don't need to go through the health code stuff as much. I can have some rats, cockroaches, things like that. People won't really care. Doesn't affect the taste very much. So, all right. Sorry if I ruined your appetite. Okay, so I think I'll go through. Well, I guess if I was nice, I would go back and forth. I'll stop here and show you. I'll show you my Vassar stats. How to do this. That would be the nice thing to do. Okay, so where's my Vassar stats? I anything here? Let's see. Oh, it's because I got this open. Okay. And I'm going to do I'm not finding my web page here. Let's see if I can go to screens instead. It's not doing anything for me either. Don't worry, this is being recorded. I'm not seeing, my Teams thing kind of messed up. My camera went bonkers recently, and I haven't anything since then. I can go to Teams. I can go to a whole bunch of PowerPoint slides. Oh, here it is. Sit here. All right, you're seeing that one? Very good. Sorry for the delay. Okay, so if I want to do a Mann-Whitney here, I'm going to go back in my slides so I can see my actual data. If I want to do a Mann-Whitney, I'm going to go over here on the left side and click on the ordinal data button. And you see when I pop up ordinal data, and you've already used this possibly when you've done the Spearman, because you can see the rank order correlation here. But I've got all three of my tests I'm talking about tonight under the ordinal data page. Mann-Whitney test, Wilcoxon assigned ranks, and the Kruskal-Wallis test. So I'm going to click on Mann-Whitney. And I have to put down, if the two samples are of different sizes, the larger sample should be designated as sample A and the smaller as sample B. Please enter the value of N for sample A. I got to go back and count how many are in sample A, which is going to be the larger one. So I've got 2, 4, 6, 8, 10, 12, 14 in one, 14 in both. So it says 28 right in the problem. But I want to make sure I got equal numbers. So 14 in one and 14 in the other. And remember, if I had, let's say, 15 in one and 13 in the other, I'm going to want to make darn sure that 15 is put down first for sample A, because that's going to be the larger one. Okay, and now I'm going to see if I want to go down here and enter the raw data I've got for sample A and sample B. 14 opportunities to enter scores. I'm going to enter these in. It looks like I got to use the tab when entering these in. All right, that's how many are in that regular group. Now I'll enter the scores for the extra virgin group. And yes, I could have had this all set up, but I think when you're showing, you want to have a video of showing people how to go through it. It's best if you enter the data yourself. That way everybody can see step by step what you're doing. All right, so I've got all 14 scores in there, and then I can simply click calculate from raw data. And just what I showed in the slides, I've got mean rank for sample A, which is the regular olive oil group, 13. Mean rank for sample B, the extra virgin, is 16. I get a Z of negative 0.92. I don't need to put negative signs or positive signs for the Z. And it gives me the probability of getting results like that, assuming the null hypothesis is true. If I'm doing a one-tailed test of 0.1788, or for a two-tailed test, which is what I ran, of 0.3576. Since this one here is not less than 0.05, I failed to reject the null hypothesis. And the research question was, does extra virgin oil improve the salad dressing? That answer would be no. And more specifically, there's no difference in terms of the ratings between those two olive oils. That's it, pretty simple. There's not a lot of output here to get confused by. Here's that U where they get the Mann-Whitney U test from. It's the one they use is a smaller U value, but again, we're not really interested in the calculation of those. So. Okay, any questions over that? I'm going to go back then.
And since what is not 0.05, we're going to reject it since the What was
Yeah,
that?
the p-values here. This p with the little 1
Yeah.
subscript, that's for a one-tailed test, and the
Okay.
p sub 2 is for a two-tailed test. And because this 0.3576 is not less than 0.05, we decide to not reject the null hypothesis.
Okay. So with this one, we still do two-tail. We still keep
Well,
it
that's what
two-tail.
we decided to do. And on the test, spoiler alert, I'm going to be telling you to do two-tailed tests for all statistical tests you use on the final. Because if I don't do that, some will read a question and say, oh, I think there's pretty good evidence there to run a one-tailed. And other people will say, well, we should be more conservative and run a two-tailed. So I don't really want to get down to that. As a researcher, when you leave this class, you have the right to do whatever you want, make that decision. But you've got to justify that a priori, which means before you do the study, collect the data, when you propose your dissertation, as opposed to defend your dissertation, you want to state all that stuff up front before you do your study. All right, is that clear? Are we good with that? All right, very good. Now I will go back and share my slides again. And there we go. All right, and I've got to advance through these quickly now because I went back and I had to look at the scores. And there's the data that we found. So that's the Mann-Whitney U test. Okay, moving along. Second problem, in the development of a textbook, see how I've got a problem now related to educators, some teachers. The authors wish to know whether the use of color photos alters the perceived readability of the text. Two passages are identified that past research has shown to have equal readability. Now, one of these is illustrated in color and the other in black and white. Both of the passages are given to a group of 13 students who rate each passage on a readability scale, 10 meaning very readable, 1 meaning very difficult to read. The readability ratings are given below. Does the use of color alter readability? So we want to know, is there a difference between having the colored textbook or just simply black and white? Some of you might think that when you go to print pages out, most printers ask, do you just want to print in black and white, save your colored ink cartridges, or do you want to fancy it up and impress people? This design is called a repeated measures or within subjects design because there are 13 students and each student is reading a passage illustrated in color and the other one in black and white. And there's two different passages. A good thing to add to this study would be to counterbalance the presentation order of these two passages. So if passage 1 is in color and passage 2 is in black and white for the first student, you might want to reverse that for the second student. That way there's not any order effects and things like that, because if you always show the color passage first and then black and white, that can have an effect on people's ratings. So all kinds of tricks with experimental designs to try to do away with effects that might nullify your overall result. All right, so these are all ratings again, scale of 1 to 10. And because we have ratings, we don't want to use a dependent t-test. We're going to use something else, a non-parametric equivalent. So we're going to use what's called the Wilcoxon signed ranks test. The data is ordinal. We have dependent samples. So rather than using dependent t, we'll use the Wilcoxon. And it's very similar to the dependent t-test, only it's going to calculate ranks again from the data to make sure we're kind of all on the same scale. See what that simply means here is that when we have imprecise ordinal scales, if we rank everything, that at least makes it comparable to each other by ranking things. And that's basically all we can do. We want to know whether the difference between the two ranks is positive, color is better than black and white, negative, black and white is better than color, or 0, no difference. This also implies then that we want to do a two-tailed test because we want to know, is color rated higher than black and white, or is black and white rated higher than color? If all we want to know is if color is better than black and white, we might run a one-tailed test, but we're not going to do that in this case. All right, so if we run this, we get a Z calculation, a Z test statistic again. And we're going to find here the two-tailed probability is 0.0688. And because once again, that's not less than 0.05, we're going to conclude, I don't know why that does it by just moving my mouse around, there's no difference between color and black and white. So now let me slip back to Vassar stats and show you how to do the Wilcoxon sign ranks. Be sure to jump in at any time if you're not following me. Okay, let's share again. And look, it says Vassar Stats website this time. That's easier to find. Okay, so let's go back now. I'll hit ordinal data again. Got to clear that. And we'll click on the Wilcoxon signed ranks test. And I've got to enter the number of paired values of X and Y. Does anybody remember how many students there were?
13.
Jason doesn't remember. Jason, you're like me. I can see something and 10 seconds later, I don't know what your name is. Yeah. Somebody
13.
said it. 13. Very good. See, there's some memory that occurs here. And I've got data cells now where I can enter XA and XB, and I've got 13. Now, it's important for me to know which one is which. So if I'm going to go back and look at my actual data, I'm sorry, I can't show you both things at once here. Color was listed first and then black and white scores. So if I enter in color here for XA, I just want to make a note of, hey, color was XA, black and white was XB, because when I get to the end here, I want to be able to try to figure out what the conclusion is, especially if it's a significant difference. You've already seen the spoiler alert that there's no significant difference, so it doesn't matter. You're going to say it doesn't really affect. There's no difference in color in black and white, but I want to know the difference. So if I start entering in this data, nope, I got to use tab again. So I'm entering all the color scores for the 13 students first. All right, those are the 13 color ratings for the 13 students, and now the black and white ratings. All right, got all 13 scores in there. Check to make sure. If I'm taking a final exam doing this, I might double check to make sure I didn't make any data entry errors, because there's nothing worse than missing a question because you entered in the wrong data. And I'll click calculate. Gives me a W test statistic. I don't need to explain to you what that is. It shows here the number of scores. You might say, wait, we had 13. Well, one of the somewhat controversial things about the Wilcoxon signed ranks test is if you have equal ranks, like you had for student number 7 here, that had 1 and 1, it rated that one the highest, it cancels that out because it's calculating the differences between the ranks and then assigning positive or negative signs those. So it says here my overall N for my data here is 12 rather than 13. You don't need to worry about that, but that's how the Wilcoxon signed ranks works. Gives me a Z of 1.82. If I would have done a one-tailed test, that probability value is less than 0.05. And I probably would have concluded something different than there is no difference. But because I did a two-tailed test, that probability 0.0688 is not less than 0.05. I conclude there's no difference. Now, suppose I would have done a one-tailed test just for the heck of it. How would I know which ones are different here? Well, we have to look at the signed ranks here, and it's not as easy as it seems, but you can see that I've got a lot more positive signed ranks. I've got 10 out of 12 of the signed ranks being positive. Well, how do I get a positive signed rank? That is if the very first one here, the first set of scores, is higher than the second one. And that's the color is the first set of scores, and the second is black and white. We're subtracting one from the other here. So if I would have done a one-tailed test, I would have concluded that color was better because overall, subtracting one from the other, I tend to get more positives, which means that I had higher overall ranks in the color group. That's it. So you have to go back and kind of look closely at your data if you want to figure out, what the conclusion is. Any questions over the Wilcoxon sign ranks test? Okay.
Would that also be true if our two-tail p-value was lower than 0.05, or yeah, lower than 0.05?
It
Would we
would,
also
yeah,
look at the
yeah.
signs?
Yeah, and if this two-tailed P would have been, 0.03 or whatever, we know there's a difference, then we have to report what is the actual difference. Yeah. And the conclusion will say something like colors rated higher than black and white's rated higher than color, something like that. Okay. All right, so let me stop sharing that and go back to my slides. Okay. Now I can advance through and show you what you've already seen. And let's move on to the final problem. Okay, finally a football example. Been waiting to use football examples the whole class. Finally, we get to use one. 5 scouts from an NFL team rated 3 college quarterbacks. Let's call those college quarterbacks A, B, and C. Their ratings were based on a scale of 1 to 10, with 10 being most effective and 1 being least effective. The ratings for the 3 quarterbacks are given below. Is there any difference among the 3 players in terms of their ratings? Now, maybe a team wants to know that because they're thinking of maybe drafting one, and they need to know, is there a real difference in terms of how the scouts feel about those 3 quarterbacks? Why does it keep doing that? I'm not clicking on anything. I just do a simple mouse over and it advances. This computer is driving me nuts. All right, so I've got 5 ratings for each of the quarterbacks, and these ratings come from 5 different people for quarterback A, 5 for quarterback B, and 5 for C. In other words, there are 15 ratings. There are 15 different scouts who are rating the quarterbacks, and this is a between subjects design in the sense that there are different people in each group, and they are not connected or related or paired in any way. So this should look very similar to a one-way ANOVA. I've got 3 groups, and I've got independents among those 3 groups. And all I want to know here in this question is are any of those quarterbacks rated higher than the others, or is there no difference? And if there is a difference, I want to know which ones are different. Now, we don't have like a Tukey HSD to follow up this, but when there's only 3, you can do pairwise Mann-Whitney U tests. You can compare A to B, B to C, and A to C if you wanted to. I won't ask you to do that for the final if one of these problems is on there. I'll just ask you, is there a difference or not? All right, so the Kruskal-Wallis H test, named for Kruskal and Wallis. We have 3 independent samples. We also have ordinal data. The Kruskal-Wallis is the non-parametric equivalent or alternative to one-way ANOVA. And if I run this, I'm going to get mean ranks for each of those quarterbacks, which is a really easy way to know which one had higher ranks than the others. You can see descriptively, quarterback 1 got higher ratings than than B and also C. But I need to know, are they statistically different? So the Kruskal-Wallis gives you an H value, which is the equivalent to a chi-square. You compare that in a chi-square table. There's 2 degrees of freedom because I have 3 groups minus 1. So I'll use a chi-square distribution on this. And I get a probability value of 0.2466. Let me ask you a question then. Is there any difference among these 3 quarterbacks? No, because that p-value is not less than 0.05. No. If that p-value was less than 0.05, I know that there's at least one difference among those 3 quarterbacks. And again, if you only have 3 groups, you can do pairwise Mann-Whitney U-tests to find out which ones are different. You don't need to do it in this class, but you could. If you have 4 or more groups, you can't do that because you violate, you'll inflate your type 1 error rate. Going back to ANOVA, I know we've used the Tukey HSD test, but once you find a significant ANOVA value, P is less than 0.05 with 3 groups, you can do pairwise independent t-tests. That's a more powerful follow-up than the Tukey HSD. The Tukey HSD is a rather conservative follow-up test. Finding a significant F ratio first and then doing pairwise independent t-tests is the same as what's called a Fisher LSD, Fisher least significant difference test. And that's appropriate when you have 3 groups. So, not that you need to know that, but this is all kinds of stuff you're going to know eventually if you end up going into statistics, which I'm expecting probably at least half of you are going to go on and get a statistics degree after this. So, Brian, you're shaking your head. I was thinking for sure you were one of those people. So, all right.
Not unless someone put the gun to my head.
Well, you never know. Never know if that happens. All right, so let's go back to ordinal data. We'll choose the Kruskal-Wallis H-test, but this isn't an active link. We have to choose whether we have 3 groups, 4 groups, or 5 groups. If you have 6 groups or more, you can't use Vassar stats. Luckily, we have 3, so we'll click on that. Please enter the value of n for sample A. Remember, that was 5. For sample B, it was 5. And for sample C, it was 5. And then I'll go down here and I'm going to enter in the raw data for each one. I've got to go back and look at my problem here so I can do that. All right, so quarterback A had scores of 8. I'm using tab again for a return. And quarterback B had these 5 scores. I'll bet some of you are amazed that I'm entering all this data and I have yet to make an error, right? Whereas, you know, sometimes old people make errors. All right, so I've got all of those 15 scores. Took me a long time. And now I'm going to hit calculate from raw data. And you can see those same mean ranks that I had listed before, 10.2 for quarterback A, 8.3 for B, 5.5 for C. I look at this H value down here, degrees of freedom, and the most important thing is I look at this probability value. If that probability value had been less than 0.05, then I know that there's a difference. I don't know specifically if A is greater than B. It's probably pretty likely that A is greater than C, but I'd have to do pairwise Mann-Whitney U tests to be able to do that. Alyssa, look at the love you're getting. Your dog is saying, Mom, are we almost done with this stupid statistics class so we can get on with our summer vacation? We are. We're almost done.
Her name is Nova, so she's been going crazy.
Yeah. My dogs are ready to go on their, I can't even say it, a W. Otherwise, they'll go nuts. So, any questions over the Kruskal-Wallis H test? Okay, I will stop sharing for that. And I think that's everything. I don't have anything more to share. I've shown you everything. Wait, did I? Yeah, the last slide was just, there's no difference with that P of 0.2466. So I don't need to share that again. Questions about any of this stuff tonight or the final? You know, pretty much. Corinne, go ahead.
So I noticed on the practice questions, there's only half of the answer key on there. Is there supposed to be a full answer key, or is there only one of the practice sets that we're supposed to do?
You mean you have a practice question document with a bunch of questions, but there's only answers for some of them?
We have 2 practice test documents and then 1 answer key, and it doesn't have the answers for both sets of documents.
Huh. Well, there should be only one. Let me see what we're talking about here. It's in modules, right? Let me see what we got for the last one here.
I have practice
You
for
know-
final 2, practice for final, and then practice for final key. And the key doesn't have both sets. It only has, I think, the practice. Yeah.
Okay. Practice for final 2. Yeah, I didn't give you a key because this is a good one to just sort, well, it actually does show a key. It shows it shows an asterisk next to some of these for the right answer. Like for practice final 2, starting with 7, 8, and 9, there's a little asterisk next to the correct answer.
Oh, I thought that was just a typo. I'm sorry.
No. It's okay. But this would be a good exercise for you to do with your team. So sorry about not giving you that. Practice 1 or final 1 or whatever. That has a bunch of problems with answer keys in the separate document. But this one, I found this extra document. I decided to throw that in there too. But this would be a good thing to go through and work through with your team. And if there's something unclear and you need to email me real quick and ask me, we can do that. Yeah. For example, let's take one here. I'm going to share my screen again and just show you what we're talking about. Let's see. Yeah, here we go. So this is what I'm looking at in Canvas, and I opened up practice for final 2, and I've got like 3 different versions of the same problem here. So for number 1 here, a company monitors the stress of its employees by administering twice a year a short stress questionnaire. Past experience has shown that stress as measured by this questionnaire has a mean of 57.4. 2 of the company's directors have just been arrested for fraud, and the company wishes to know whether this event has increased stress in the company. It administers the questionnaire again to a random sample of its employees and obtains these scores. What statistical test is appropriate to answer this question? So yeah, I don't have this set up multiple choice with a key, but some of you looked at this immediately and said, of course, this is your chance to shine, by the way. You don't need to be shy anymore. Just go ahead and just look at that and say, the appropriate statistical test is one we've already studied, and the name of it is, I'm not sure why you're delaying. Perfect opportunity to show off.
I'm rereading the question because when you read it, it was kind of fast. So
I read for speed, not for understanding.
Is it a 1 sample t-test?
Yes, who said that?
I did.
Brianna, you get all the points for today, which is the same as what other people are getting. But yeah, that's good. We've got a population mean of 57.4. We're going to be comparing a sample mean to that population mean. Yeah, very good. Let's go to the next one. Same thing. Company monitors stress. Company wishes to know whether this event has increased stress in the company. It obtains the scores of a random sample of its employees, both before and after the fraud arrests. So here's before the fraud arrests and after. What statistical tests?
Is it a Pearson correlation?
No, because if we were doing a correlation, first of all, we'd have to have paired scores. And this very first before arrest, after arrest, this isn't the same person getting the 56 and the 53. If it were, that would be very important for us to know. But we have a random sample before and after the arrest. So these are all different people before and different after. So we have independency there.
So it would be Spearman.
Well, Spearman and Pearson are a correlation. They want to know, again,
Oh,
if you
yeah.
have pairs of
it's
scores,
independent.
which we don't, but a correlation is you want to know is as one set of scores goes up, does the other one go up or down?
Okay, independent t-test.
Independent t-test, yes. Independent t-test.
Wouldn't 3 or the next one also be independent t-test? Because the next one mentions having 2 separate random samples. I read that previous one as one random sample that was
Oh, a
met with
random
twice.
sample of its employees both before, and you're right. This one obtained a score of 2 random samples, one that completed the questionnaire before and one that completed it after. Yeah. So this one is more specifically stating that there are different employees in the before group and after group. This one is less clear, but it's saying a random sample, and then you're questioning them before and after the rest. So this 56, 53 probably represent one person. Yeah, very good. Hopefully there won't be a confusing question like that on the final. That'd be very controversial. So going through these 3 questions, I'm sure your confidence level now for the final exam is sky high, right? So what you need to do to prepare for the final is not going to have any questions on there that you haven't seen before in terms of the type of test. The challenge is it could be any of the tests that we've covered in this class. That's what's called a comprehensive final. So there could be a 1 sample t-test. There could be a Kruskal-Wallis test on here. There could be a Spearman test. There could be a chi-square test of independence. You have to go through and study those problems and see if you can figure out which test to use. So it's one thing to know what test to use, and then you also probably have to know how to do that test and how to reach a conclusion. So if I were on a team with one of you right now, and being the great team member I am, I would probably ask AI to come up with 10 examples of chi-square goodness of fit problems. I would ask AI to generate 10 Spearman correlation problems. And then I would share those in a random order with my classmates and say, let's study tomorrow night and see if we can approach these together and figure out which tests we would use and how to get the right answer. That way you're prepared for everything. Because there will not be any tests on there that you haven't seen in this class. So there will be nothing new, but your challenge will be how to distinguish between different tests so you know what's the appropriate one to use. You guys have been killing this class, been crushing the quizzes, been doing well on the exams. I mean, I can tell you right now, you don't care whether I do this, but next summer when I'm changing the course a little bit, I'm going to make it a little harder. I'm going to add, I'm going to have 6 questions on the quiz, add 1 more there, and I might add a few more questions on the tests because you're killing them and you're getting done too early. You've ruined it for everybody else. So
I'm with Brianna. Can we look at number 7?
I guess if we have time. All right, here we go. Yeah, number 7. School administrator wish to determine whether support for a new suspension policy different among people according to their ages. He surveyed 20 people in 5 different groups. Is age related to whether someone supports the policy? Which of the following conclusions is appropriate? Okay. Well, looking at the options, it seems that this comes down to only a couple of different types of tests, right? It could be maybe a chi-square. Then you have to know whether it's goodness of fit or test of independence. And it could be an ANOVA, right? Now, there are 5 groups, but there's only 1 score for each group. You can't really do an ANOVA with 1 score in each group. And those are really frequencies. That's, how many people support the policy of the groups. So what do I do here? I've got 20 people in each of 5 groups. Is age related to whether someone supports the policy? How many categories do I have here if I'm doing a chi-square? 5. this isn't like a 2x3 or something like this. This isn't a test of independence. I don't have rows and columns. I just have 5 different groups. Yeah. And how would I calculate the expected frequency for each of those 5 groups? Would it be 20? Since I surveyed 20 in each group? Not 20 because
Wouldn't it be divided evenly between the 5?
yeah. So
4?
I'd have to add 10 and 12 and 15 and 19 and 18 and then divide it by 5 because my expected frequency always has to equal my total observed frequency. That's how I would get it. Yeah. If you do that, you'll get one of these options. Probably the one with the asterisk. Age is not related. Chi-square greater than 0.05. I've got more problems here for you. So, but yeah, study these with your teams. And if you run into problems, just email me and say, hey, we're all on Teams right now. Would you join us? We're going over this right now. Can you join? I don't really have much of a life. I could probably jump on Teams and join you. If I'm not walking a dog or dealing with dogs, stuff like that, I could probably get on there. So yeah, you have a little less than 48 hours to prepare. So I would devote some time tomorrow definitely to doing that, and maybe even Thursday before you take the test. Your teams are strong. Everybody's got good teams here. Do you like, how many of you really dislike your team? Raise your hand. No one's going to say that. See, yeah, find the people who have been helping you all the 5 weeks and allow them to help you better understand things. And then contact me if you need help.